In this video, we're going to perform the continuity of CPC and polarity test, a combined test, and then follow it with the insulation resistance test of this lighting circuit that we've wired using a conduit looping method. Now, this video is part of a bigger series, which I will leave a link for in the description below, so you can check out that playlist if you've jumped into this video. In previous videos, we've done the wiring diagrams of this conduit looping method, which is a slightly different way of wiring lighting circuits than the 3-plate method we often attribute to working, say, in a domestic dwelling. So in another video, I talked about the rig and whether you wanted to build one at college or at home and all the parts that make up that rig. And then we went on to wire this one-way lighting circuit. So from the consumer unit, we've got this office number 1, say, lighting point here, controlled by this switch here, using that conduit looping method. So in this video, we're going to carry out those dead tests. We're not going to go live with this installation. I never go live with it with my learners. It's that first 10 weeks, and can we start working out how to perform a continuity test? In other words, measure the resistance of the circuit and record it in the appropriate box heading R1 plus R2, and what do they mean? And then follow it off with the polarity. In other words, does the switch operate the lighting point in here in office number 1 and turn it on and turn it off, and then leave it in the on position, put the covers back so we can perform that insulation resistance test. So in the next part of the video, I'm going to set up my tester ready to do that continuity test. So we've got a multi-function tester, we've got our Megger 1711, and we're going to be measuring the resistance of the circuit during that continuity test. So if you've got a slightly different tester than me, you're still looking for the omega symbol or ohms, and that's a scale we need to set it on in order that we can measure the continuity or the resistance of a conductor. So if I rotate that round, we'll see our machine comes on, and it's a case then of sorting out our leads next. So our machine's on and working. We've got our leads. Again, we need to do a bit of a visual inspection of these before we use them. So just have a little once over, check there's no nicks or damage in them. Okay, as you get those leads out of your box. And that's really important in a college setting, that you have a good once over on those leads, even though it is a dead test. If they've damaged the leads, obviously it's going to cause a problem with the results. So we've got our leads, and I'm going to be using the red and the green one. If you've got a different color lead or a different end, it doesn't really matter, but we like to keep them logically with color. And that's also with the connections in the top of the 1711. We're going to be using these two here. So it wouldn't matter what color leads we had, but we're going to be using the red and the green section here. And we always like to keep them the same, don't we? So we're going to put the green one in the green, but it wouldn't matter if it was the red. And obviously the red one in the red, it wouldn't matter if it was the green. So we've got our leads ready to go. And now we're going to remove the resistance of these. Well, we've currently got the tips on them, which I will use, and I will use the crocodile clips as well. But just for removing the resistance, I'm just going to swap them over to the crocodile version of the leads, and then we're going to start by removing the resistance of the stuff that we're going to be using in circuit. These leads themselves are made up of copper, so of course they offer resistance and will need removing. And in early videos I did on the channel, I used to use a link like this in order to link in my consumer unit the line and CPC together. And I use those, so I would have to remove the resistance of these crocodile clips and obviously the link here that offers resistance. But I've moved away from that recently and started trialing this, which is our R1, R2 link. Okay, so I'm started using this for a college setting especially, because this end here is magnetic and will go onto the top of my MCB for my lighting circuit. And then I've got a crocodile clip here, which I can link onto my earth bar when my CPC is connected. But of course, I must remove the resistance of these as well. So if I insert them into my leads, it doesn't matter which way around they go. So I've got those inserted there. So I've now got the resistance of the leads and the link all in circuit. We heard the machine make a beep. Our continuity reading is 000, so it's saying it's already zeroed out. If that was a flashing 0, we would be below 0, but at the minute that's saying 0. Well, let's clear that by pressing the test button. So let's press the test button once. You notice now we have a reading, so that would be a reading that would need to be removed. How to remove the resistance of the leads? There's a test button on both sides of the machine. It wouldn't matter which one we pressed. So if I press this one just here, we press it and you see we've got 0. So we've removed the resistance of both the leads, the crocodile clip and this link. So we're ready to perform the continuity test where we'll measure the resistance of just the conductors in circuit and not the resistance offered up by the leads and the link. Just take the consumer unit cover off. Again, in a college setting, it's really important, especially where they're not captive screws, that we keep hold of the screws. So if you lose them at college, it becomes a very difficult task, obviously, to replace those in order that we can secure the cover in place. So what I'm going to do is undo mine, And I've done a full video on how I made the connections using PVC singles within this consumer unit. And again, if you haven't checked that one out, it's worth checking that video out. And we talked about torque settings as well. So I'm going to take these screws that held the cover on, and because I'm not using them, especially at college, let's pop them back into position. So for this test, the continuity of the CPC, we're going to perform it where we also do the polarity test at the same time. So we're going to need to link together in the consumer unit the line conductor under test to the circuit protective conductor. So I need this circuit here linked to here. So it's a dead test. We've got no electrical energy in here. There's no cable, there's nothing, it's not connected to anything. So if it was, of course, there'd be the safe isolation procedure and loads of other stuff we discussed on the channel. But this is a test that we carry out really early on in that first 10 weeks. There's no electrical energy in here and it is a dead test. So I'm going to link between the top of the circuit breaker and the earth bar, and this is where this R1, R2 link comes in handy, because this one here is magnetic. So you can see there, if I just drop it on, okay, it just drops onto there, and then if I get it in position, it just sticks into place. So that's connected, and we can link it to the earth bar where our CPC is connected. And that's shown in the on-site guide as well, isn't it? It's shown linking together the line conductor under test to the circuit protective conductor under test to carry out this combined continuity of CPC and polarity test. We will be measuring the resistance of both the line conductor and the circuit protective conductor. So when we record this result, we record it under the continuity box heading R1 plus R2. R1 being the measured resistance of the line conductor added to R2, which is the measured resistance of the circuit protective conductor. So by linking the two together, our reading, which will be in ohms for our continuity test, will be recorded under the box heading R1 plus R2. R1's the line conductor and R2 is the CPC. We now need to move out into the installation and test at every point in circuit, and we need to record the highest reading achieved wherever that is in the circuit. We said in a previous video that this straight skirted batten lamp holder would better be unassembled in order to probe on to do the test, because it becomes quite tricky to make those. However, at the end of the lesson, I said to people to rebuild this because you didn't want to lose the parts. So I've come back, I've had a break in a session, I've come back and I'm now going to test for this continuity of CPC, including the polarity test. I'm going to unassemble my straight skirted batten lamp holder to make it a lot easier for me to get onto the actual terminations for the connections for the test. So if we break that down, and we can see that we said in a previous video that this is actually got no polarity because this takes a bayonet cap lamp, so it doesn't matter which one of these is line and which one of these is neutral, and it would be a switching line and neutral. However, if you had an Edison screw style lamp, you would have only one center pin and the screwed section would be a different conductor. So the center pin, if you only had one, would be the line and the screwed element would be the neutral. But often at college in the early days, you're using lamp holders that take bayonet cap and these have no polarity. So when I look this side, it doesn't matter which way round the blue and the brown ones were, so there's no polarity to these, but it's deadly important that we got the circuit protective conductors in the right place. And hopefully you can just see there the symbol for earth. So our CPCs were connected in the back section, but we didn't have an L and an N or a SL and an N for our switching line and neutral connections. So it doesn't matter which of these that we have them which way around. So we've got no polarity at this lamp holder. We're going to test between the switching line conductor and the CPC here, and then we're going to operate the switch at the same time to prove it comes on and off. There are adapters that can go into the end here, so you could get actually onto the final pin, or you could try and push onto this pin. Remember, this is a test that we're carrying out very early on, first 10 weeks, and we're just looking to go through the fundamentals of a continuity of CPC and polarity test, and we make it more advanced as we move through our levels towards our endpoint assessment. So we're going to be testing between our switching line and CPC here. We're going to get a reading in ohms, we're going to operate the switch, and then we're going to see the fact that it will get full scale deflection, and then we'll leave it in the on position next. So I'm going to probe onto my circuit protective conductor and my switching line at the lamp holder. It doesn't matter again which way around our leads go, but again we like the green one to go on the green and yellow one. So onto my circuit protective conductor and onto my switching line. And I've got a reading of, when it settles down, 0.06 of an ohm. So that suggests that we're getting a resistive reading, a completed circuit. We need to remember that reading, but at the same time, we also need to operate the switch. So at the minute the switch is closed, we have a low reading and therefore it would be in the on position. But in order to do our polarity check, we need to make sure that we operate that switch. So I'm going to operate the switch. If I put my hands in a more comfortable position, I come down to here to operate the switch. So down at the minute it's on, so that's quite logical. So that should go off. And if we look at our reading now, it's gone greater than the machine can read. So we've got an open circuit. So the circuit is currently off. In other words, we've broke the line conductor. Let's remake the line conductor. And we see our reading slightly different now of 0.09. That's due to the resistance of the actual switch blades. These don't get used that often. So sometimes when you operate them a few times, you can see that reading change. We're going to stick with that reading there of 0.09, and we need to remember that. And we've left it in the on position as well. So we've left it on, ready for our insulation resistance test. However, I said we need to check at every point in circuit. So we've checked at the lighting point. There is only one other point in circuit, which is the switch. We need to check at the switch next. And of the two readings, we need to record the highest one wherever that is. So we proved the CPC got to here, and we proved the polarity of these connections here by visually looking at them. We confirmed the back section was for the earth symbol for the CPCs, and we knew that it didn't matter which one was line and which one was neutral, so we've done that as part of our polarity check. We also operated the switch when we were there, and we've left it in the on position, also part of the polarity check. When we're down at the light switch itself, all we need to prove is the CPC gets to here. It's a fully insulated system, so the CPC is here in case we change it for a metallic electrical part, which is an exposed conductive part. So it could be that we had a steel conduit, steel box and metal front, and therefore they would need to be connected to the CPC and prove that they are. And we've done that in previous videos as well. So I've made this little 221 Wago connector with an extra link on it so we can make the test. And this here will be used in later videos to extend the circuit. So of course people are saying, why didn't you just go on that end? I could do, but I've used the Wago 221 and I've put an extra little link on it so I can use it in the future to extend the CPC as we create the circuit that goes on to do office number 2 and office number 3. So at the minute I need to prove the CPC gets down here. So let's change back over to a crocodile clip. Let's make sure we get a nice connection onto here. So a nice firm electrical connection there. And then we're just going to go on and pick up our line connection. It doesn't matter which one we go into. Remember, we left the switch in the on position. So it wouldn't matter which one we went on to. So I'm going to go on to L1. We get a reading of 0.06 of an ohm. So we've proved that the CPC gets down to the switch. So we know it gets all the way down to here where we've connected into our Wago 221, and we've picked up our line connection from the switch and we've left it in the on position. So I've left that in the on position. That's really important when we get to the insulation resistance test, which we're going to carry out next. I now don't need this little additional lead here, but I'm going to keep my Wago connector on there for future extension of the circuit. I'm going to need to put all my covers back on. So I need to put all these back into position and rebuild my straight skirted batten lamp holder so everything can go back into place before we carry out our insulation resistance test next. So let's rebuild our straight skirted batten lamp holder. We put it in, it goes into one position, it actually locks in there. There's two little sort of keyways that mean it sits firmly into position. So base plate on first, followed by our ring. Just make sure it winds down nice and easily so you can see that spins easily so there's no cross threading going on there. Firmly into place, and then the skirt. And then this is the thing that I really want to reiterate to learners, is how to support it against these boxes here. This is a Conduit T-box, and the thread in here takes an M4 screw. Not a wood screw, an M4 screw. So we're going to push it into position. I'm going to find my M4s, and these are here, these brass M4 screws, in order to hold it in position. So it's important that we use the right ones. Too many times I've heartbrokenly seen someone using a wood screw in order to secure it into position. So down they go. Locate that into position, and that's my straight skirted batten lamp holder down. So just tighten that one off. So that's it in, so it's in position. I'm also going to put a lid on this corner because obviously we've got single insulated cables there, and if we're doing it properly we should make sure we put the box lid down. I know in a college setting often this gets missed because obviously we're not going to go live with it, but it is good practice to practice doing it correctly. So that box lid can go down as well. Once we've got that one into position, we can then reassemble our light switch next. So that will need to screw down. So all of these need to be in position before we can carry out that insulation resistance test. So light switch next. So now to hold the light switch in position, we're using these 3.5 machine or box screws. So they're different to what we had at the top. So we've got to make sure we get the correct screws in the correct position. Just going to make sure that we curl the cables in neatly into the back of the box. and then we'll hold that in position. I do know, and we've said it in previous videos, obviously we've got a square box and a round light switch. That's obviously not perfect in the real world, but this is a college setting, and while we're using plastic ones, we're using plastic ones because obviously we've got a lot of those for inexpensive in college, so we're going to use those in this system. More often than not, this would be metal clad, and it would use a grid mounting system in order that we can obviously get those in position. So there we go. So that's it. So this is screwed down nice and tightly. Maybe I'll just bring this one into the parallel position as well. So let's bring that through so we can just turn them into the same position. And we're ready to do our test. This is in the on position. All covers are on, and we're now ready for that insulation resistance test. So in order to carry out our insulation resistance test, we need to come back to our machine and change the scale. We're currently on the ohms scale. We're going to stay in ohms, but this time it's going to be in the megohms scale. Often on the channel, I still call it megohms, and I always get picked up on it. That tends to be a bit of a slang, doesn't it, for megohms. So I'm going to move it to the megohms scale. And now there's 3 voltages to choose from. For our system, we're going to test it at 500 volts DC. And the on-site guide says that we should achieve a minimum insulation resistance of 1 megohm. However, further investigation at 2 megohm. But if you look in the guidance notes 3, it says for a brand new installation, it shouldn't be less than 20 megohm. Okay, so we've got a brand new installation. I expect the insulation resistance reading to be very, very high. I've done a separate video explaining about insulation resistance and length of conductors, and again I'll leave a link for that video if you haven't already seen it. So for this test, it's 500 volts DC. We're in the megohm scale, often called megohms, and we're going to be expecting a reading very, very high, possibly an infinity reading, or one greater than the machine can read, as we measure its insulation resistance. Just to prove these leads haven't been damaged during the first test, I'm going to short them together on this scale. So I'm going to remove the tips, and I'm going to put the crocodile clips on. I don't want to get my hands on the end of here. If I was going to touch both of these ends here, I would obviously pass 500 volts through myself. Remember, that's 500 volts DC. So I'm going to link the two together. I'm going to press and hold my test button now. It doesn't automatically do this test. And as they're joined together, I've got 0, 0, 0, in other words, a dead short, meaning that leads are in good position. If these leads were snapped, and again, I've done a little video on them, and they tend to snap around here, what you end up doing is obviously getting equivalent of it being broken. If I press and hold the tester again, you get a reading greater than the machine can read. So if we're going to short them together to prove that they're not broken, we expect to get 0 or a dead short for that reading. So our leads are good, and we're ready to test with these. I'm going to change between tips and probes, but let's look at the consumer unit first. Now, we haven't got the tails in here. We know the installation is completely dead. This is an early test that we're carrying out. As I said earlier in the video, if it was a board that was energized when you arrived, there's tons of safe isolation procedures before you carry out this test. But let's think about the things that we must make sure are in place before carrying out this test. We said that the switches, and there's only one in circuit, needs to be left on. The lighting point is back and covers are on, but the lamp itself has been removed. If we had the lamp in here, it would be connected across the 2 pins, and that would be switching line and neutral, and would cause you an issue with your reading. So all loads need to be removed, because loads are naturally connected across line and neutral. All switches are on, all covers are on. So if we look in here, these are also effectively switches. So we don't want these switches in the on position either, because these components here, so this one here being an RCCB, contains electronic components, and we do not want to pass 500 volts DC through those because they could be damaged. So we're going to make sure everything is in the off position, and we're going to test from the outgoing side here with these off, because if we left it on, the 500 volts would pass up and through the circuit as well as down and across the bottom of the RCCB. So we leave everything in here in the off position. Now, I've left one little conductor here, which you can see doesn't go anywhere, for a reason. This is to remind you that when carrying out the insulation resistance test, the earthing conductor, which comes in with the tails, must be connected and connected to the source earth, as well as any bonding. So in a TNCS earthing arrangement, this green and yellow conductor would go off and be connected the cutout where the neutral is. And in a TNS system, this goes to the sheath of the cable. If there was an earthing terminal, an MET, this green and yellow earthing conductor would go there, and the bonding must be in place. So if the circuit has bonding to gas, water, oil, etc., all of the bonding conductors must be connected in this earth bar as well. I know at college that's probably not going to be the case, and you're not going to have these in place because obviously it's not connected to the electrical system. But the sooner you hear the fact that when you carry out your insulation resistance test, the earthing conductor and bonding conductors must be in place and connected when carrying out the test, it helps you move through your levels on your understanding and knowledge. So I've left the earthing conductor in as if it's connected to the source earth for this test. There is no order in which to carry these out, not even a Gary order, so it doesn't matter which way around we do it. So I'm going to change one of these over for a probe. So I'm going to connect between my earth bar, and it doesn't matter where I go on the earth bar because they're all connected together in a brass bar. So anywhere on the earth bar, at the top of my breaker, and test between these here and here. I want to press my test button. I need to press and hold it. I've got a reading greater than machine can read, greater than 999. The symbol on the end is the greater than. I like to put plus in my test paperwork, so I would put plus 999 megohms, okay, often called megohms. So that's the first one. We're going to now test between the earth bar and the neutral bar. So if I move my probe across to here, press and hold firmly, and then press the test button once again. And we can see we've got a reading greater than 999 megohms. And then finally, we need to test between the line and the neutral. Again, it doesn't matter which way around your test leads go. So I'm going to test on the line connection and where the neutral is. Again, it wouldn't matter where I go. So I know that's the terminal I'm testing, and people get obsessed with putting it on top of there. This is a solid bar, so it wouldn't matter where I probed onto. So I'm in those positions there. I'm going to press and hold. And again, I've got a reading greater than 999 megohms, often called megohms. Okay, so greater than the scale of the machine can read. So a lot greater than the minimum accepted in a BS7671's on-site guide of 1 megohm. Certainly greater than the 20 megohms suggesting guidance notes 3. And we would expect this reading to be massively high. So what we're trying to prove is that the insulation around our conductors has not degraded between them. So we don't expect these to have broken down over time, or perhaps friction caused them when pulling in to rub against each other, and the insulation between it is starting to break down. These are brand new cables. We expect it to be a fantastically high reading, and we got a reading higher than the machine could read, and we would record those readings for me as plus 999. But sometimes people use that greater than symbol. But again, I like to put plus in there. So that's the insulation resistance test carried out. So there we've carried out our continuity of CPC test. We included the polarity at the same time. So in other words, we confirmed the conductors were correct at the lighting point, and we switched it from the switch on and off to prove that part of the polarity. We also know the brown conductor was connecting to the top of the MCB, all part of that polarity check. We record our highest readings wherever we achieve it in circuit under the box heading R1 plus R2, and we measure it in ohms, and we got a reading of 0.09 ohms, and R1 stands for the line conductor and R2 stands for the CPC. We then put all our covers back on. We left our switches in the on position. We made sure we didn't have any loads in circuit, so in this case the lamp wasn't connected, and we carried out that insulation resistance test, expecting to have a very high value. We don't expect the PVC to have started to break down or deteriorate over time, and we got a reading greater than the machine could read. We were a little bit careful with that test because obviously there's electronic components in our RCCB, and we made sure that our devices within the consumer unit were off. The power wasn't connected to the consumer unit, but we started discussing the fact that we do need in the real world a connection to the source earth, and I simulated that with our earthing conductor being installed and protective bonding if it was in place. So all of those need to be in place when carrying the insulation resistance test. I know we're only about 10 weeks into our course, but the more times we can talk about the correct way to carry out tests, the better as our knowledge progresses on throughout the years. So as always, I hope this video has been some help.